So welcome to the last lecture of the week. I want to talk about a formalism, a very popular formalism in the supersymmetry literature. It's well adapted for dealing with supersymmetry in 4 dimensions. It's not a formalism we're going to use at all in this module after the lecture today, and so this is an optional lecture for those of you who are interested. It may be useful for you if you're trying to approach some of the literature in the field. So the idea behind this formalism is to take advantage of the fact that in even dimensions we have these Weyl representations, which we can use to reduce the Dirac representation. We can use it to reduce the size of the dimension in half, right? So in 4 dimensions, 4 space-time dimensions, we have these 4-dimensional Dirac representations, and we can decompose them into two-component Weyl representations. So again, the idea here is to use the Weyl representations instead of Dirac. So in 4D, which is where this two-component formalism works, what we're going to do is we're going to write our 4-component Dirac spinner as a 2-component spinner a 2-component spinner lambda with an index A, and a 2-component spinner chi, actually we'll call it chi bar with an index A dot, where these indices A and A dot, or B and B dot, they run from 1 to 2. Okay? And now we'll work furthermore in a particular basis. We'll work in that basis I mentioned a few lectures ago, where the gamma matrices are strictly off diagonal. So I've got a generalized Pauli matrix sigma u, and it's bar in the upper right and lower left hand corners, and then sigma mu is the identity, and then the other Paulis, and sigma bar mu is minus the identity, and then the other spatial Pauli matrices. Now the gamma 5 matrix is diagonal in this basis, with ones and then minus ones, and so if we act with gamma 5 on lambda, we'll find its positive chirality, and if we act with gamma 5 on the chi, we'll find its negative chirality. And I'll make another point here, which is that the indices are often not suppressed in this notation. And they give you some extra feeling and intuition for how things go together. You never want to contract a dotted index with an undotted one, for example. And also the dotted ones we're always going to use for quantities we think of as the barred quantities or complex conjugates, whereas the undotted ones we'll think of in terms of the regular quantities. And so we'll see as we go on why I've decided to bar this spinner chi, how it's natural to make that a barred spinner as we proceed. Okay, so this is how the formalism is set up, and now let's see how our inner products interface with this formalism or decompose under this formalism. So for example, we could consider psi bar with psi, which as we discussed is psi Hermitian conjugate gamma 0 with psi. And now gamma 0, remember, it's formed from these time-like Pauli matrices, which we decided were just the identity and minus the identity. And so when we contract psi bar with psi in this basis, what we're going to find is we're going to find lambda dagger chi bar for the first component, and we're going to find minus chi bar dagger lambda for the second component. So these off-diagonal ones are going to mix the lambda and the chi spinners. And now to reintroduce these indices, what people usually do is they call this lambda a dot bar, chi bar a dot, minus chi a lambda a, where we've in a sense defined lambda dagger to be lambda bar a dot, and we've defined chi bar dagger to be chi a. So again, when we talk about the complexified or complex conjugated quantities, we use the dotted index. The unconjugated quantities, we use the undotted index. Okay, so this is example 1. Now let's do another example. Let's look at the Majorana inner product. See how that looks. So for that we need to know what this charge conjugation matrix is in this basis. Let's choose minus I, gamma 0, gamma 2, gamma. And if we expand that out, I claim what you're going to get is you're going to find minus I times the diagonal matrix, which has a sigma 2 and a sigma 2 in it. And so notice when I multiply I by sigma 2, I basically get something that's purely real, right? I basically get this completely antisymmetric tensor with a 1 in the upper right and a minus 1 in the lower left. Okay, so let's see what happens. So I've got psi transpose C psi. So I can write that as lambda t minus I sigma 2 lambda plus chi bar transpose minus I sigma 2 chi bar. And this is going to be what? This is lambda A. And then let's call this I sigma 2, let's call it this antisymmetric matrix, epsilon AB, lambda B, plus chi bar A dot, epsilon A dot B dot, chi bar B dot, where I'm defining epsilon AB and epsilon AB lower indices to be 0, 1, minus 1, 0. And similarly for the dotted guy, A dot B dot is epsilon A dot B dot is equal to 0, 1, minus 1, 0. Okay, so that's what we get. Now, I want to add a slight wrinkle at this point. I want to think about this epsilon tensor as a kind of metric on my spinners, a way of raising and lowering indices. And that actually presents a small problem because I ought to be able to use the epsilon tensor to raise and lower its own indices. And now I have a slight inconsistency having defined both epsilon with upper indices and lower indices the same way. And so to get around that, let's introduce another matrix so we don't get confused with what this epsilon completely antisymmetric tensor should be. Let's introduce a matrix lowercase c AB with upper indices. Let's call that 0, 1, minus 1, 0. And we'll use the same formalism for A dot B dot. But when we have a lower index, we're going to introduce an extra minus sign. So that's going to be 0, minus 1, 1, 0. And that's going to be the same as C A dot B dot. And so when I write it in this way, what I had on the previous slide, this spinorial sandwich, this psi transpose C psi, I can now write it as lambda A C A B lambda B. But now I need an extra minus sign if I'm going to replace it. The other guy, because I had the lower indices, let's call it C A dot B dot chi bar B dot. So I'm in fact not going to think of epsilon AB as the metric, but as CAB as the metric. And now everything is consistent because I can raise and lower C's own indices with itself and everything will work out. The signs will work out in the way they need to. Okay, so I have that. Let's use this tensor to raise and lower indices. We can write this as lambda A minus chi bar A dot chi bar A dot. Can do one more just for old time's sake. Let's look at what happens to the Lorentz vector. Could do psi bar gamma mu psi, which is the same as psi dagger gamma 0 gamma mu psi. And now expanding this out, I claim I can write this as lambda bar A dot. And now the gamma matrices get replaced with these generalized Pauli matrices. So I'm going to get a sigma bar with upper indices, A dot B, lambda B, and then chi A, sigma mu with lower indices, they're mixed indices, chi bar B dot. Very good. And again, you sort of see how these extra indices here are giving you some information about how different objects can get joined together. Okay, the last thing I want to do before bringing this lecture to a close is discuss the Majorana condition in this notation, which has a nice form. So the Majorana condition in our notation was that psi star is equal to B psi. And in this Weil basis, B is going to look like minus I gamma 2 gamma, using our, say, C conjugation matrix from before and acting on it with gamma 0. So that gets rid of one of the gamma zeros in C. And so what I might find then, I'm going to find component-wise that lambda star is equal to I sigma 2 chi bar, and chi bar star is equal to minus I sigma 2 lambda. So, I mean, the way to think about that is, right, the gamma 5 matrix, I know how that acts on the spinners. It's going to give me a plus or minus 1. And then that I gamma 2 matrix, that reduces to I sigma 2 acting on the two components. And it will mix them, right? It will set lambda equal to chi and chi equal to lambda. So reassociating indices with this, I'm going to learn that lambda star A dot, I use the dotted index because it's a complex conjugate. That's C A dot B dot. That's what that I sigma 2 is. Chi upper B dot. And then I have chi star A. So I've got a double complex conjugate. So that gives me the undotted index. CAB, lambda B. And now let's use that C matrix to raise or lower the indices. And so at the last step here, I'm going to learn that lambda star A dot is chi bar A dot, and chi star bar A is lambda A, which looks roughly consistent. So the Majorana condition is saying that lambda star is chi bar. So it's a relation between these two components of this 4-component spinner. as we knew from the earlier lectures. All right, so that's all I want to say about the two-component formalism. I hope this gives you a taste. It's a very incomplete taste. Again, we're not going to use that going forward, but maybe some of this will make other literature that you've come across or reading or interested in reading, it will make it more accessible. So join me next time. We're going to come back and start discussing supersymmetry for real. We're going to talk about representations of the supersymmetry algebra.